We're going along the path that we followed with linear motion, describing what changes the motion, changes the speed, changes even directions, and we can look at force, energy, and then we had a situation where we were starting to talk about energy conservation and momentum conservation. So in the linear case, this is all very familiar, F equals ma. Our kinetic energy is 1/2 mv squared, and our momentum, P, was equal to mv. Okay, well, in the rotational, so this is linear case, that should look familiar. Rotational, you know, we turn everything into Greek letters. So in rotational, this became sum of the torques equals I alpha, kinetic energy equals 1/2 I omega squared. So angular momentum, as it turns out, we describe that with an L, either a capital or a lowercase l. Your book will use both. And instead of m, we put I, and instead of v, we have omega. And it shouldn't be a surprise that these are substitutions, because if you remember, the connection between force and momentum in particular was that the sum of the forces is equal to the change in momentum with respect to time. And if we do the same thing here, we've got change in the torque. The sum of the torques is equal to I times alpha, but alpha we can write sum of the torques as equal to I d omega dt. If your moment of inertia is constant, you can plug that in. This becomes I omega, or the sum of the torques is equal to dl dt. And so this is again the more general expression of Newton's second law, just like this was the more general expression of Newton's second law. So for rotation. Now, when momentum was conserved, right? Momentum conserved, we said it was conserved when we had a system, at least in the linear case, where the sum of the forces, the external forces on our system, were equal to 0. In other words, we could isolate a system, because that meant if I got a 0 over here, this derivative was 0, which meant this P, this momentum, was constant. And so it shouldn't be a surprise that if the external torques to the system are equal to 0, then that implies that the angular momentum is constant or conserved. Now, an instance that you're familiar with is an ice skater doing a twirl. And so you have your skater as a stick figure with arms out, spinning, so pushed off, provided some torque for her himself, and started spinning. So having a spinning omega, I'm going to set it up so that omega is upward. It's hard to tell which direction that circle's going, but you can use your right hand rule and set that up for yourself. And as she or he brings their arms in, so they bring their arms in close to their body, what happens is their omega gets bigger. They spin more rapidly. And so if they spin more rapidly, what we do is we say, hey, this is a system. This is my system. What's happened is I had I times omega initially, and that's my momentum, is the same afterwards, the moment of inertia, because the arms aren't out as far. Remember, our moment of inertia is proportional to mass and r squared. So if your arms are far out, you have a bigger r, so you have a bigger moment of inertia. So this is a smaller moment of inertia, so it must mean a bigger final speed. And so you can figure out how the moment of inertia has changed by how much the speed has changed, the angular speed, number of revolutions a second. And you've seen this when you've seen ice skaters take their arms in a spin and then pull everything in, and the spinning just really picks up. Okay, and what they're doing is they're taking advantage of conservation of angular momentum. They're decreasing their moment of inertia, which increases their angular rotations, right? Their angular acceleration. There is some torque, obviously, inside the system, but we don't need to calculate it. We don't need to calculate the force that's required to bring the arms in, the change in energy, any of that. Okay, but we can ask about the energy, so we might as well do that here. The kinetic energy initial is 1/2, I'm going to do this big I, omega I squared, and we're going to compare that. Kinetic energy final is 1/2 little I, omega, big omega F, squared. And so to compare these, what is constant, what is the same, is this is equal to this. So if I set this up, I can write this as kinetic energy initial equals 1/2 big I omega initial, like that. And I can compare that with my final, which is 1/2 little I big omega F times a big omega F. I think I may be off screen, so I'm going to rewrite it over here. Kinetic energy initial equals 1/2 big I little omega I initial. And then kinetic energy final is 1/2 the small I big final speed times the big final speed. And what you can see is that these parts are equal to each other, right? This part in parentheses. So this final kinetic energy is actually bigger. So the skater has increased their kinetic energy. So there must be some form of internal energy in the system. So in this case, this is a case sort of like our collisions where we don't know anything that's happening really inside the system, but what we can say is that it's isolated. There aren't any external torques that we need to worry about if we can ignore mostly the friction from the ice. That will tend to slow this down over time. But the kinetic energy, the mechanical energy, is not conserved. We don't know what the torques were that were applied, but we can find still something about the final speed.